today. Let's evaluate together the global latent workspace in embodied agents and see if we can bridge consciousness and AI. So I want to start with motivation. So why is conscious AI research important? So I think maybe somehow counterintuitively, first it's important for the well-being of biological systems. So why are we here, right? What are we doing here? Why are we doing science? Why are we doing philosophy? Because we want to create a better world. That's our goal, I think, at least for a lot of us. And so general artificial agents can help with this. They can help us make better science, better philosophy. They can do tasks that we don't want to do, and they excel. So something like the jack of all trades, they can do already like card games, robotic manipulation, and multimodal language processing. So this is possible, but still there's something missing. And what is missing? So it's at least conceivable that this is consciousness, because from the animal and human point of view, we know that if we're not conscious, then we are definitely impaired for certain complex tasks. So the second motivation, I think, is the well-being of artificial systems. So we are, it might be possible that we are creating consciousness down the road. We don't know that yet, and we need to make sure, I mean, that most people here are aware of that. We need to make sure that we're not creating mass suffering. And on the other hand, there's also the diametral ethical obligation, maybe. So if AI can have forms of consciousness which are kind of super blissful, which is something which we cannot even imagine, then we might have the obligation to actually create this on a mass scale as well. Although this doesn't sound very romantic, but if we can create something which has amazing experiences, then we have the obligation to create this, one could argue. So how can we even start making conscious AI? So I think the starting point for this clearly at this point are neuroscientific theories of consciousness, the closest to the source. And so there's a vast landscape now, which is something good, I think. So there has been, the last decades, the science of consciousness field has been blossoming. There are theories all over the place, and that is great. However, this is also a little bit much. Yeah, not all of these can be true. Only if they would all be subsets of each other or something like this. So we need to try to unify and prune where possible. So today I want to unify two of these theories. One is the global workspace theory, which says that information becomes conscious when it gets famous in the brain. So something like a frontal parietal hub connected via long-range axons in both directions, makes information conscious when it comes from specialized processors, gets integrated into the hub, and then broadcast across the brain. The sensory-motor embodiment theory, on the other hand, is not so much a local theory. So it doesn't say so much about where consciousness would be localized, but it says more about like what would be the metaphysics, so to say, of consciousness. And this embodiment plays a role here in that they say, okay, it's actually about sensory-motor invariances. So as an example, if we take the blind person, which we took electrodes on the tongue, and we connect the electrodes to a camera, and the blind person walks around, then this person can actually perceive a kind of visual space. This seems to be that it's not really the location of where it's happening, but it's somehow the way it is processed, and which might relate to sensory-motor relations and the shape of the body then in that sense. So now to the global latent workspace. So let's first have a schematic overview. So again, we have these processors mobilized into the conscious workspace. And now we just substitute these neuronal processors by specialized machine modules. So from this, we have then the global latent workspace where they can all communicate with each other. This has been proposed by Ruffen van Rooyen and Ryota Kanai. And so we can have something like a neural translation, which leads to semantic grounding if we connect visual processing with natural language processing, or even affordance if we connect visual representation to motor outputs. So now this is so much to the schema. So, but what would be the concrete? What would the concrete implementation look like? So here, look at the model architecture. Again, what we need is we need to broadcast and we need integration. So this information has to have the same format for all of these specialized modules. Otherwise, they cannot talk with each other. So we have here minimally 2 modules and the global workspace that connects them. And we set this up as follows. So in the team with Ruffin, von Rohlen, we have in the middle the latent representation, which is connected to the modules through encoders and decoders. And these networks are trained via 4 losses. One is the translation loss, so we want to be able to get from one module to the other. Second is translation loss in the other direction. Then, I mean, it's basically the same loss function. Then also we need not just broadcast, but also a representation which is as similar as possible, right? So they kind of need to speak the same language, the modules. So we have a contrast loss that that both encoders have a similar central representation. Then demi-cycle, so this is semi-supervised learning, so this would be unsupervised. Just get back the same output you have from both sides, and then whole cycles. So from both sides go the whole way around. And I'm not going to talk about this here into detail, but this enforces that we can have broadcasting and optimal integration properties. So one use case for this is fast semi-supervised semantic grounding. This is now I'm first going to talk here about some things which have already been implemented before coming to the new things working on right now. Here we have a vision and a language module. If we put on a visual input and a language input, so we train this on some corpora pairs, then we find that actually the translation, so get from vision to language or from language to vision, becomes 5 times quicker to get there. So in terms of number of bimodal sample pairs, you need 5 times less when you have this semi-supervised, so these cycles in there. Then the global workspace shows cross-modal knowledge transfer. So what does it mean? We have a vision module and an attribute module. And if we take here the visual input, for example, some camera input, and the attributes of the position of a robot and the goal position, then we can, so first we train the global workspace again like before on the vision and attribute side. So we freeze the workspace and then we train, for example, now we just take the vision input and we train the reinforcement learning policy to get us to the goal. And now if we just take in, if we use the attribute module, we find that we get the same, that the same policy will, so we have 0-shot cross-modal transfer. We just put in the attributes and we get the same policy. This is cross-modal knowledge transfer then. So then the second, so what I want to talk about most today is the semantic grounding through affordances. So not just through language, but even through sensory motor embodiment. So first, what does this mean, affordance? So Gibson coined this term. It means I mean by affordance something that refers to both the environment and the animal in a way that no existing term does. It implies a complementarity of the animal and the environment. So here, this really means what can I do with my body with this thing in front of me? It's not just the visual input, but it's also my bodily shape which defines this. And so why can this be helpful? So we can have a clustering of sensory scenes. To see this, first, this has been shown for a standard reinforcement learning model. So this is trained in a kind of complex 3D jump and run environment where you have some simple puzzles and so on. And then the representation somewhat close to the action probabilities can be used. And if we look at them, if we look at how similar they are, depending on the visual scenes in a 2-dimensional space, then we see that actually there we get some kind of clustering. So this has been done by a colleague. So there's some kind of clustering of visual scenes which afford forward movement, like this arrow means you can go a level up, or backward movements if there's a wall. So there's some, so the visual scene is kind of clustering, and this clustering is kind of not only dependent on the visual lighting conditions or something like this. So how would these affordances look in the sensory motor global latent workspace? First, to find this out, so we do this in two steps. First, we train a reinforcement learning model, like before, the same structure. And we see, okay, in the beginning, I mean, yeah, just go a little bit how this looks like. So because I think it's interesting, it's kind of like sometimes I feel like, I want to help you. So it's kind of like this animal-like feeling. And then, so we're getting there at some point. And when we have the kind of, when we have the data of the visual input and the matching action output, we can use these and then train our global workspace with this data. So here we then use the motor latents. From the visual input, there's a variational autoencoder. So we have latents from both sides and train the global workspace with this. Now we can look at the affordances that we find. So we find that these are globally accessible. I mean, that's why we have this workspace, and they are locally structured. So what does it mean? It's for the vision module and the central global latent representation. For the vision module, the vision module is a variational autoencoder. We look at the latent representation here, and we see that if we color these data points related to if it's forward or backward movement, then there's not really any structure in there. However, after the training of the central of the global workspace, we see that the central latent representation really has well-structured differences, so which should make downstream processing easier. And the same also goes for the other action possibilities, like right slide, left slide, get structured. These are conjunctive clusters, so you can go forward and left or backward and left and so on. And interestingly, if we look again at the shape of the clusters of this reinforcement learning agent, so we can say that from the visual to the reinforcement learning, there's some clustering, but especially so it seems that the global latent workspace structure really helps to focus these sensory motor clusters. And this is clustering process that it helps doing this clustering process, which is then helpful for further downstream tasks. So some example scenes just to see that this is working. So we have, if we look at forward in the green part, these are visual scenes. We see that they're really quite different, but they all afford the same movement. And similarly for backward scenes. And just for the accuracy now of the global latent workspace, so how accurate is this? Is this for the motor affordances? Indeed, we see that. So if you look at the ground truth is discrete. So run forward would be 1, no run 0, and run backward -1, for example. And in the colored distributions here is the motor latent distribution. So the latent space is continuous. And we see that this is not too bad. Also together like 80% accuracy. And interestingly, what I can only shortly talk about here is that we also have a visual generation prediction accuracy. So if we recall, here you can go from the visual side to the affordance side, but you can also go back from the motor latents to the visual side. So you can really generate or predict, how you want to call it, visual scenes. And there's quite some variance in the accuracy of this. This is still analysis in progress, but at least so the principle is working. And so what I want to say, what we find in the end is really that we have embodied global latent sensory motor representation in the global latent workspace. And if we look at this in action, so we go from the vision to the motor side, and at the same time the motor side can predict the next visual input. And so this seems really very similar to what the sensory motor theory would predict, that there are some sensory motor laws which the architecture tries to find, and which should be sensible, of course, also in a functional way. Again, this is really an embodiment principle. So if you're not Yes, thank you. If you're not, so sensory motor affordance, sensory motor invariances always refer to some bodily structure, because how the sensor changes depends on how the motor affects the body, and how the body is geometrically positioned in space. And so for this theory, there's a lot of experimental evidence. Here some interesting findings with mice, which have been reared in the dark, and then upon first finding a visual input, when the visual input is coupled to motor input versus non-coupled, so some random input, we find that the visual system is much worse processing, is much worse developing. So the recurrence here is quite strong, and nevertheless, there has been so one of the main critiques from the sensory motor theory is that, well, okay, I can be so it's possible that I cannot move, but I can still be conscious. So how does this work? And so what we find here is really that important is that there is a latent representation, and latent really in the sense of hidden, so that you don't need the connection to the motor module anymore. You can, you even don't need the vision module anymore. That's also how you can imagine of imagery or something like this. So this is really a standalone process once it has been integrated into the nervous system or a computational system. Another interesting point here is if you look at concerning linearity of the world, or as we perceive the world. So something like a straight line, for example, regional simulation versus cortical representation. So the cortical representation is highly nonlinear, and it has been shown for deep neural networks, for example, that if you have nonlinear activation functions, you get a strong transformation of the manifold, so that you can, for example, have a linear separation of theretofore not separable data sets. And this might be very important for us. And so this could relate to, so again, I want to stress this fact because it seems to be something like we seem to take this for granted, that, well, actually the world is kind of like a matrix multiplication and just like a linear representation. But it seems impossible if you think about it, because the brain is highly nonlinear processing. So why should we think that there's a linear transformation of something out there? So this really seems to be some embodied complementarity, which has been shaped by the body into really the manifolds, which then appear in the computational systems. Yes. So to conclude, and outlook and open questions. So first, global latent workspace is unifying. So we have seen that we can unify the global workspace theory and the sensory motor theory of consciousness here. Then it's functional. So affordances reduce the complexity of high-dimensional sensory space, and in a functional way. And these sensory motor representations are not only globally accessible, but also structurally localized. So global always means like, it's everywhere. No, it's not everywhere. It's somewhere localized. It's still bounded somewhere so that other processors can use it. Then outlook for future work on this would be a combination of a reinforcement learning model and the global latent workspace model. As we recall now, we have trained them both separately, or used the reinforcement learning data to train the global latent workspace data. And the idea is now to bring these together and do an end-to-end learning and see how this fares and its performance in comparison. And finally, some open questions. So what about codependence of sensory motor manifold learning, semantic understanding, and spatio-temporal reasoning? Spatio-temporal reasoning is still something which even vision language models and similar are not perfect at yet. Maybe sensory motor manifold grounding topology there can help in really having intelligence in this sense. Maybe this is important really to get intelligence off the ground. And finally, relating to consciousness. So if we have such an embodied global latent workspace, would this be enough for phenomenal spatial perception? So is the system conscious? And if not, then why not? Yes. And that's it.